Hi, everybody, and welcome to this webinar on API security, how to shield your APIs right now to stop the bad guys abusing them. I'm going to be joined today by two colleagues. Richard Taylor is the CTO of Approov and the co-founder, and Skip Hovsmith is the principal engineer with the company, and he also leads the US team. So we're going to go through a number of things here. First up, Skip's going to take us through some recent breaches and recent attacks and use that really to illustrate the difference between exploiting vulnerabilities in your APIs and the abuse of APIs. Richard's then going to talk through the different attack surfaces, and he's going to really look at it from the perspective of an attacker, how they move between these attack surfaces and gather information and then mount an attack on your APIs. And we'll also talk about the mitigation strategies that you need to employ to counter those attacks. We'll give a demo of the product, and then we'll have some Q&A. And if you hang on till the end, you'll see we have a special offer for you. So do stay with us. Thanks. And without further ado, I'm going to hand over to Skip.
Thanks, George. Can you see the slides?
Yes, we can.
Okay, great. Hello, everybody. The objective of this first section here is to try and help you understand what we see as the difference between API vulnerabilities and actual abuse of APIs, and hopefully a better appreciation for how you should defend against both of those types. So our CEO, David Stewart, challenged me to work in a recent, oops, I'm having trouble advancing my slides. That's odd. There we go. Okay. All right. So our CEO, David Stewart, sorry about that, was commenting and challenging me to see if I could work in my Half Dome trip into this conversation. So on Sunday, I had the good fortune of being able to hike Half Dome in Yosemite Park with my middle daughter. She's wanted to do this for about 5 years. And access to the cables, which are over here on the left, are regulated by permits, and permits are really hard to get. So we lucked out on Friday. So at 1 in the morning on Sunday morning, we left from the San Francisco Bay Area, traveled to Yosemite, and by 5:30 in the dark, we were on our way hiking to the top of Half Dome. So what does this have to do with API abuse and vulnerabilities? Well, the last 400 feet or so is this climb up these cables over here on the left. It's a crazy ascent, and you're usually not locked into the mountain in any way. So it's a free climb up. And if you consider my human API of walking and climbing, the question is that abuse of this API or not? Is it mental or physical abuse to actually try and do this and climb up to the top? Alternatively, there was a woman that was climbing near us, and in the section in the subdome climbing up to the cables, she actually ripped the sole off her boot. This, I would say, is a actual vulnerability. It's something that was a design flaw built into her boots. So using the universal duct tape, she was able to tape her sole up, and she continued to ascend up to the cables. I'm not sure I would have had the guts to do that, but she made it all the way up to the top. So this is the money shot over here to the right. It apparently was not too much abuse, and my daughter and I suffered no vulnerabilities. So we made it to the top, and we made it back down. So we had a good time on Sunday. So looking at apps, there really are some trends over the last number of years, going from a traditional sort of browser-based type interface, where you have a browser making HTML calls into a server, which is fetching basically UI and presentation information mixed in with data, and serving presentation information back to the browser. So everything's kind of jumbled up, and most of the logic for making decisions is back in the backend server. You can contrast that with the trends in mobile apps and in single page web apps, where much more of the business logic is now being held over in the device. The presentation is all being handled In the case of mobile apps, over on the mobile app, it's built into the app itself. It's not being fetched each time with a browser call. The calls tend to be much finer grained because the business logic is over on the app itself. You're making many more calls using structured APIs to get data and bring more data over into these apps. Additionally, most of these calls for scalability reason are going to be stateless over at the back end. So if you're a hacker trying to attack this type of app, because these are stateless, there's less restrictions in terms of the order that you make these calls and what you do as you're experimenting. So these are unfortunately the easiest type interfaces to hack if you're trying to get into somebody's backend, because they're so well structured and they're stateless. So I'm going to start with a vulnerability here. OWASP publishes a number of top 10 vulnerabilities in 2019. The first API security vulnerability list was published, and the #1 vulnerability on the list is broken object level authorization, or BOLA. And if you look at the diagram in the middle here, typically what an attacker would do would be to go ahead and reverse engineer the API as best they can, and make a legitimate looking call. They would log in using credentials that they have and go ahead and make a call. If it's successful, then they'll take what is the object reference. In this case, might be a user ID type reference or a resource ID, and try a second resource ID or a user ID and see, can I extract information that I really shouldn't be authorized to extract, say in a patient database? Can I get information about other patients by simply fooling around and randomizing that ID number that's in the place? So this is a very common type of vulnerability. As an example, I wanted to go back to sort of an old favorite of mine. Back in 2017, there was a vulnerability on Instagram where you could go ahead and capture a password reset request API call, and you could simply replace the user ID that was attempting to be reset with somebody else's user ID. So you could pick a celebrity's user ID if you wanted to, and the backend would not actually check to see if the user ID that was being requested to be reset had been authorized with credentials from that same user ID. So people use this to go ahead and hack into Instagram accounts of celebrities and go ahead and take over. And the symptom you would see as a celebrity whose account has been hacked is you would go in and find out that your password doesn't work anymore. And that happens to us periodically, and you'd probably just go ahead and issue another password reset, take control of your account again with your new password. But in the meantime, whatever sort of dubious photos that there might be sitting up on Instagram could be published, as they were to this particular celebrity back in 2017. So that's a good example of a vulnerability. Now let's look at something that's more classified as an API abuse. So a year ago, Rashik Shahid, he's a big fan of the ice cream machine at McDonald's, and I didn't realize it, but the ice cream machine apparently is very finicky. It's a very finicky thing, and it's not uncommon for these machines to be down. If you look at the diagram on the right, you can see all the red dots are machines that are not serving. So if you're a soft ice cream fan, you'd like to know ahead of time whether the ice cream machine at the McDonald's you're going to is working or broken. So he actually hacked into the API. He got in the middle and looked at it and was able to work out the mobile phone's ordering API. And initially he started out placing orders to every McDonald's in the US and spending what would have been the equivalent of over $18,000 every minute to place these orders. And if the order went through, he knew the machine was up. And if the order was rejected, then he knew that the machine was down. And before actually consummating the orders, he would then go ahead and cancel them all. This was detected by the McDonald's service as being a denial of service attack because it was too high. So he's since lowered that down, I think, to about every 30 minutes he goes out and probes across the US. And it's quite a popular app. So the thing to notice here is that there's no particular vulnerability in the app itself. There's no problem with it. He's just using it in a way that wasn't really intended to extract information from that. So in this case, McDonald's kind of has a hot-cold relationship here. So sometimes they're promoting it and saying, if you really love ice cream, then this is an interesting app for you. And other times, I think if it was able to take down or slow down the rest of the ordering process in the system with a denial of service type effect, you wouldn't be so happy. So this is a good example of API abuse. There's nothing wrong with the API itself, but the context in which it is used is questionable. Credential stuffing is a very popular attack style on the web. And in this kind of attack, you're going to go ahead and use credentials you have gotten your hands on in some way. If there was a breach of one site and you were able to get a list of passwords, and go ahead and try that in an attack site that you're trying to go after. And this succeeds because most of us are pretty lazy. We tend to use our email as our username, and we tend to use a very similar password each time through. So an attacker simply takes as many lists of information they can get their hands on, sets up some scripts to go ahead and try and log into the victim service. And if they're successful, not only have they proven that the credentials are correct and can be applied to this new site, but they also may have gathered some additional information just by the return information on the login. So they can build up a new list that is qualified for the site that they're attacking, and either exploit that or sell that on the web. And this is amazingly an amazingly popular attack style. You can see Akamai did a study on their CDN back in 2018, and there were over 27 billion credential abuse attempts that they were observing just on that particular network in half a year. So here's a recent, during the pandemic, incident with Zoom. Zoom obviously became quite popular and had quite a few attacks directed at it. This credential stuffing one back in April of 20 was just strictly a by-the-book credentials attack. They went back and gathered some databases off the dark web, going back as far as 2013. They scripted up and ran these against Zoom, and they were able to establish over 500,000, I see I have a typo there, credentials which went on sale in April of last year on the dark web. And if you acquired these credentials, then you could potentially certainly take control of an account, impersonate the person who owns the account. You could launch new meetings, but perhaps more clandestinely, you could eavesdrop on what was going on, or review past recordings to extract intelligence and information there. This was a very standard, typical, unfortunately, type of credential stuffing attack. And so there's plenty more where this came from. So really, in reviewing sort of vulnerabilities versus abuse, when your API is up live in production, the challenge really is to prevent it from being abused. Hopefully you have squeezed out all the vulnerabilities in earlier testing, and you're now looking at, is the context for this API access correct? So in the example above here, we have a app trying to call into a backend service. And because the app is legitimate, it's not a hacker going through, the app's going to be calling at a fairly low velocity of API calls. And each app will be able to access or modify a few pieces of information, per minute, say. So it's a very controlled situation, and the sequence of calls is relatively predictable. If you contrast that back to a scripted attack using a bot, if you can successfully make API calls by using scripting, then you don't have the restrictions that the app sort of gives you in terms of the order, sequence, velocity of these calls that are being made. You can set up many parallel calls and really raise the velocity that you're making calls at. And you can very quickly go through and crawl through a database and extract information or place a bunch of orders or do whatever damage you want there. So it's really important at runtime to make sure that you're focused on preventing API abuse. And we're going to discuss that in a little more detail in the next couple sections. So what it really comes down to is, I think we see in the press a lot of wise advice about shifting left, meaning let's do more work trying to improve our API security at development time. You see talk about DevSecOps, for example. And that's all good, but that's primarily focused on getting the vulnerabilities out of the app itself. It doesn't per se prevent you from doing any kind of API abuse with, say, for example, these credential stuffing attacks. So the runtime protection that's required, we like to call shield right. So shield over and protect your APIs. Make sure the context that those APIs are being called at is correct. And I'll pass this over now to Richard Taylor, who will give you a little more detail and information on how that is done in the marketplace and how we do it specifically.
Okay, hello everyone, I'm Richard. I am going to carry on from where Skip left off. Okay, so I'm going to talk in a bit more detail about the attack surfaces, especially in kind of mobile apps and communication with backend services. So if we think of the type of system we're trying to protect here, we have a mobile app that obviously has a user, and that mobile app probably has some kind of API key in it, and the user themselves will have some kind of credential, and this is communicating with the backend API service using TLS, so the communication is encrypted. And I suppose traditionally we tend to think maybe that the attack surface is of the API itself. And that might be protected by a web application firewall, API gateways, it might be sitting behind a CDN, etc. And then we have all sorts of technologies which are used to protect the security of the user in terms of typical username, passwords, and then translation of providing those credentials into an OAuth 2 token, etc. And we may use biometrics as well. So essentially the service is checking that the user is authorized, and basically that typically there is also an API key which is being presented by the mobile app in order to get access to the backend service. So if we think though about what an attacker might do if they are trying to find ways of getting vulnerabilities in the API or thinking about ways to abuse the API, they would go through the process of looking at the mobile app. And obviously one of the issues with a mobile app is that essentially the code that is being used to access the backend API service is being published. And therefore anything to access that backend service by definition has to be in the code. And in many types of services, it's easy for a user to kind of sign up. So typically the hacker will sign up with some anonymous email address and have the user credentials, and then they can use the mobile app to access the service. And because the mobile app is in the public domain, there are a whole plethora of different tools that you can use to actually unpack what is inside the code. So there are various, both for Android and iOS, reverse engineering tools that you can use, like APK tool and JADX, which does Java decompilation. There's Hopper, for instance, as well, that does disassembly on iOS, and various static analysis tools which look at the contents of the app itself and perhaps can extract secrets from the app. So for instance, if there is an API key inside and it's not very well protected, then it's relatively easy to extract. You can also take an app, you can reverse it, you can potentially make modifications and republish the app and then basically run it on your device with those modifications, which perhaps will be providing some kind of output and still access the API. So that's one avenue you can take. The other avenue is, of course, an attacker has control of the device that they're running on, and therefore they can use routing and jailbreaking tools. So there are many of those too. Magix, for instance, on Android, enables routing of a large number of different devices. There are many iOS jailbreaks out there nowadays as well, covering a multitude of different versions. And once you've jailbroken or rooted a device, then you really have complete control over it. And that enables you to install various hooking and instrumentation frameworks. And these type of frameworks allow you to run the mobile app, maybe as is, but find particular points inside the app where you can hook a function. You can see what's going on. You can see the data that is being passed between the mobile app and the backend API. In fact, there are kind of scripts available that basically hook at the HTTP transfer level. So essentially, you're seeing all the transactions that are occurring. You can look inside the user interface. You can see how the data is being generated. So even if there's some level of obfuscation or hardening going on in the mobile app, then you can sort of gain a picture dynamically of what type of calls the mobile app is making, and what kind of credentials it's passing to the backend API in order to make those accesses. And yeah, the third thing you can do is you can insert yourself in the channel itself. So even though the channel is typically encrypted between the mobile app and the backend service, that doesn't prevent you, especially if you have a jailbroken or rooted device, from inserting yourself as a man in the middle in that channel. So in that case, what you're doing essentially is using one of these tools like MITIM Proxy or Burp Suite or HTTP Toolkit. And that essentially is a tool that sits between the mobile app and the backend API in the channel. And from the perspective of the mobile app thinks it's talking to the server. And from the server's perspective, the server thinks it's talking to the mobile app. But what actually is going on is that you're probably using a self-signed certificate that you've pushed onto the mobile app. So it starts to trust the channel, even though it's actually communicating with the man in the middle. And the advantage of that is you can basically see all the traffic going between the two. You can capture the traffic, you can replay the traffic, you can modify the traffic, and quite often in terms of poking around in an API, that might be where you start, is you capture some real transactions that have come from a mobile app, and then you might try modifying the transactions. You can look for kind of these types of bowler vulnerabilities by modifying device IDs of different types, user IDs. One of the protections there is against this, which I'm going to talk about a bit later, is that you can do a thing called pinning in your mobile app, which basically tries to lock down the mobile app so that it will only trust certificates from the service you're trying to connect to, even if additional trust anchor certificates have been pushed onto the device. Although on a rooted or jailbroken device, that can typically be defeated as well, although it is a good additional protection. So from a hacker's point of view, the steps really are, as we're sort of saying, there's this kind of reconnaissance step, which is really the aspects I've been talking about so far, where you break open the mobile app, you analyze its code, you analyze its dynamic behavior using instrumentation tools, you maybe analyze the actual traffic using a proxy. You try and understand what it's doing, try and understand the shape of the API. And then once you've done that, that enables you to move to the next step, which is essentially this kind of weaponization step, where there are different approaches. And amongst our kind of customer base, we've heard stories of all different sorts of different approaches. There are approaches where you build a script that basically emulates what the mobile app does, so you can talk to the backend API service as if you were the mobile app, and the service can't tell the difference because you're using the same keys, you're using the same signing algorithms or whatever is used to protect the requests. You might modify the app. Like I say, you can do a reverse engineer, make some modifications to the code, republish the app, at least to run on your own device. And there are other occasions where actually you're using the original app, but you're basically running it in maybe in an emulator farm. You may be using it in a rooted device where you are dynamically hooking what's going on. So you're making minimal changes to the app, but you're perhaps using Frida, for instance, to hook certain requests, modifying the requests on the fly. So essentially you can control what the app is doing without having to completely rebuild an entire client application. And really then, as Skip was talking about, there's all sorts of different attacks, at least from that. You could be trying to exploit vulnerabilities in the backend API. You might be credential stuffing against login endpoints to try and gain access. You might be running some kind of bot farm to somehow abuse some of the functionality that the API has by creating a farm of new users or scraping information from the API itself to be used elsewhere. And in some cases, we've seen occasions where you basically reverse engineer it for the purposes of building into a different app to be published. So for instance, a service could turn up as being available in some different app, perhaps aggregated with competitors. So if we kind of step back and take this holistic view, I mean, we started off with attack surface 1, which is basically the vulnerabilities in the service or the vulnerabilities in the API itself. But there's actually other various other attack surfaces we actually need to worry about as well, especially from this API abuse point of view. There is the attack surface of the integrity of the channel, and are the requests that are coming from the mobile app being modified or monitored in any way. There's the attack surface of the modification of the app. Is the app actually the app you thought it was? Does it maintain its integrity? And there's the attacks on the device that the app is running on. And there's the attacks against the user credentials, either because somebody with the intent of hacking the API is signing up as a user, or because credentials are being used in some kind of credential stuffing attack against the backend API. So to come back to the point that Skip was making earlier, there are these two styles. There's this attack of the API itself, looking for vulnerabilities inside the API. Bolo vulnerabilities being a kind of classic example, but there are many others. Another example that's seen quite commonly is excessive data exposure, where an API actually provides much more data than is actually exposed in the app itself. And unfortunately, the exposure of that data could be damaging, or it could be used in alongside some other analysis to kind of produce some kind of data, effectively a data breach against a user. I mean, you see this in terms of providing additional personal information or perhaps additional location information for a user that may not be shown inside the app, but it is actually provided from the API. And that really is a vulnerability of the API. But in terms of the API vulnerabilities, that's one thing, but there's also this whole other area that you have to be aware of, which is attack by automating access to the API into a client that is able to essentially exfiltrate the data. So it's not constrained by the user interface that you put inside the app. It can take all the data from the API and then it can use it however it wants. And typical types of attacks might be a data scraping attack, where data can be exfiltrated from the system and then perhaps published on the website. So going back to Skip's previous point, there are two levels of protection that are essentially required in order to kind of cover these types of issues. There is the need to shift left, which is essentially get rid of the vulnerabilities in your API by adopting better development practices, more testing, to make sure those vulnerabilities in the API itself are not there to start with. But there's also this need for shielding, because shielding prevents API abuse, and actually shielding also prevents being able to use any vulnerabilities that exist, because the reality is that you can't shift left immediately. There will be some time before all the vulnerabilities can be fixed, and even if the vulnerabilities are fixed now, there's always the possibility that there could be a vulnerability in the future. So having a shielding layer as well is also a really good practice. So in terms of what needs to be shielded, effectively, it has to be everything between the user and the surface. What essentially we're doing here is we want to kind of expand the sort of trust envelope from the service right out over the communication to the mobile app, onto the mobile app itself, ensuring the integrity of the mobile app, and also looking at the integrity of the device itself. So really the shield also needs to be looking at what type of device it's running on, looking at, are there other things running on the device which could be a danger to the app? Is it running on a booted device, etc.? So really you have to look at this as a whole and be able to shield this so that you know that the API requests that you're actually receiving are from this kind of shielded source. Now, the kind of big technical challenge here is that you want to shield all these things, but what can you trust? And the sort of answer is you can't really trust anything between the user and the service, because of course all that is really in the public domain. You're just seeing a HTTP request coming in that's connecting to your backend service. You can't really tell, you can't really believe anything that HTTP request is telling you. So you really have to verify using a technical means. You have to verify that every API call is really coming from a genuine, untampered instance of the mobile app, and that given that app was actually running in a safe device environment. And of course, you can't really tell that until you know that the app itself is genuine and therefore is reporting that correctly. And then you also have to know that there is no interception going on in terms of the TLS between the mobile app and the backend service. So if you can guarantee these things, then of course you have the advantage that you can block all the scripts and you can block modified apps, and that can happen even if those API requests are coming in with perfectly valid user credentials or a perfectly valid OAuth 2 user authorization token. So in order to do this, you really have to be able to build this trust level in. And to do that, you, as well as the user authentication, you really need to have strong app authentication. So if we go back and look at for inspiration, we kind of look at the kind of aspects of user authentication which are possible. There are these kind of classic 3 factors. So in terms of user authentication, you have something that the user knows, like a password, although we know that by itself isn't very strong. That's why you kind of have these other factors. And you might have something you have, which might be a device authenticator app, or it might effectively be access to a particular phone number. So basically possession of a SIM, which enables you to receive an SMS code, which could be used as a second factor. And then there's also the something you are factor, which typically is sort of biometric. So it could be, for instance, a fingerprint. So you're proving that the user is there because there's something inherent about the user which you're proving at runtime effectively by providing your fingerprint. So if we think about this from the point of view of app authentication, there is the something you know aspect is essentially this API key which is embedded in the app. It's like a password essentially for the app, but we know that actually that could be quite easy to extract. So it's not very strong. There is essentially a type of possession element that you can have with an app in order for it to be able to prove itself, which is typically a sort of binding that might happen when you first install an app and you first onboard. You might push some keys down into Keychain or Android Key Store, which essentially is a binding to the device. But of course, the weakness with that is that there's the onboarding step. And before that onboarding step, there isn't really this possession aspect. And then finally, there's the something you are, which is the stronger aspect. And in the context of apps, we would see that as being remote attestation. So this is basically the app proving to the server that it really is the app. And this is through a kind of cryptographic proof. So we basically see this remote attestation as being like biometrics for apps. So it really takes a kind of shielding to the next level. You're proving to the service that you really are the correct app calling the service. So that, of course, leads me nicely into a discussion about Approov, which essentially is providing this remote attestation element for mobile apps. So I'm going to kind of provide a quick overview of how Approov works, what it does, and then actually Skip is going to provide a very quick demo after that. So how Approov works is essentially shown here. So there's two parts to the technology. There's an SDK that goes inside a mobile app, and that's the part that proves to the service that it's real, it's genuine. And then what that's talking to is a cloud service that we run, that runs on AWS. It's an API service that runs continuously. So in terms of using it, the first step is, well, you integrate the SDK inside your app, and then you publish your app as normal into the App Store. But also at the same time, you use a configuration tool to say to our cloud service, this version of the app is an official app. Please recognize this as an official app. And then when the app starts up, when it wants to make its first API call effectively, what happens is that the Approov SDK talks to our cloud service, and there's a communication that goes on there. And essentially what that is doing is proving to our cloud service that it is the real deal, that is actually the correct app. And it's also providing information about the runtime environment it's running in. So this is the remote attestation element. And then when that's happened, when API calls are being made to the back end, the API, an Approov token is added automatically to the request, and then it goes over a PIN TLS connection to the backend service, and then that can be verified. So the token itself is actually a sort of standardized JOT token. So it's basically a cryptographically signed token that has come from the cloud service that says, yes, this is the real app and it's running in the environment, which you've considered to be okay. It's a very short-lived token because it doesn't require any kind of user interaction. We can basically refresh this in the background. So typically the tokens only last for 5 minutes. In terms of integration, we support a whole range of different front-end integration approaches. And there are obviously many different ways you can write apps. The idea is that we integrate right into these different types of frameworks, and we integrate essentially into the HTTP stack. So you make your API calls as normal, and as a side effect, we pin the connections for you, and we also add the Approov tokens. In the back end, it's actually very simple. We do support many different languages and different back-end systems, but it's actually very simple in that you're essentially just checking this industry standard token. The Approov SDK itself, because it's doing this remote attestation element, it's basically doing measurements. So I suppose so rather than containing secrets, it's basically being challenged by the Approov service to basically do measurements of what's going on inside the app and also what's going on inside the device, and provide those measurements to the cloud service, which sort of then decides whether it's okay or not. The important thing is that the tokens that are used to access the backend API are signed by keys which never go anywhere near the app. So basically the remote attestation happens, and then if it checks out, the token is passed to the app, so which can then pass it on to the API. So there are a whole load of different security mechanisms we use in the SDK itself in terms of its sort of protection, and its protection against it being manipulated in any way. And it's essentially doing this advanced memory scanning analysis, looking for root jailbroken devices. And we also have this optional integration as well that enables you to use things like Android Safety Net and iOS Device Check, which go right down into the trust zone, so into the hardware security layers inside the operating system. Because all the communication is happening live with the back end, we're able to provide live data. So you can basically see your apps running, and you can also see what's happening inside the apps, what type of things are being detected. And because of that, you can also change your security posture over the air in real time. So you can decide, which apps are registered. You can also decide whether, for instance, you allow rooted devices or not, and also various fine-grained aspects of which particular types of behavior or frameworks on the device which you allow. We also simplify the pinning process. One of the reasons why pinning sometimes isn't implemented is that it basically binds an app to a particular certificate in the back end. And the problem is, if that certificate were to change for any reason, then it means the app can no longer connect. And if you can't reestablish the original certificate, then that means your app is no longer working. So there's a sort of distinct danger with pinning in your app if you are concerned or not completely in control of when the certificates will change. So one of the things we also offer is that we can do over-the-air updates of the pins. So essentially, you can pin your app and get all the security features of pinning your app, but we can basically update that over the air, so there's no risk of breaking the app effectively. So that's a very quick intro to Approov. So with that, I'm going to hand back to Skip, who's now going to provide some quick overview of how it works in practice.
Thank you, Richard.
I need to stop sharing.
All set. Okay, I'm going to walk you through a sort of virtual demo of what's going on with Approov. So over here on the right, I have a simple app. I'm going to go ahead and start that up. So this is simply a simple toy app we use a lot for demonstrations, just fetching a bunch of different shapes. It's talking through a cloud to a backend shape service that is just responding with random shapes whenever it's requested. So let's just imagine that you've got this application, you're going to market with it, and you want to add this API shielding through. So why would you want to do that? Well, as Richard's already described, there are fraudsters out there that think that getting shapes is a very valuable and profitable thing to try and steal. So if they were going to start to attack this app, as was described, because it's an app and you have lots of tools to analyze it, one of the first things the attacker might do is grab your app from the App Store and do some static analysis and see, can I find some API keys? Can I find other goodies of information that it can help use to understand the API and to actually go ahead and try and take over those calls? Additionally, if the TLS channel is established, you would like to believe that everything is encrypted and fine, but unfortunately, because as Richard described, you can inject trust into the mobile app itself, you can successfully pull off these man-in-the-middle attacks. And therefore watch and observe all the API traffic that's going back and forth. You can harvest API keys there. You can reverse engineer the API quite easily. So if a fraudster does succeed at getting that, then they're going to start probing. They'll start slowly, and over time they will go faster and faster to try and get more and more information out of your backend service, and then they will back off to try and stay sort of just under your detection radar screen. So at this point, you would have come to Approov and say, I need to kind of shut this stuff down. And what you would first do for step one is to go ahead and drop the Approov SDK into your application. At this point, a couple things have happened. The SDK is now communicating up to the Approov cloud service. It's establishing a secure connection here. It's also starting to pin the connection here to your Shapes backend service. So it's done great so far. The one thing that hasn't occurred yet is that you haven't actually registered your app with the service. So though it's communicating to our service, we don't actually recognize it as a legitimate authentic app. So we are returning tokens to you that indicate that the service itself is or the app itself is not authentic as far as we know. The app itself doesn't know, it's just getting tokens, and what it's going to do is take that token and pass it onto the backend service where you'll check the token and determine if it's okay. So at this point, if we were to go ahead in the backend service and enable Approov checking, then the bots themselves, which have no tokens, or if they stole tokens, they're not valid tokens, they are immediately shut down. But unfortunately, so is your app over here, because the app has not been recognized by the Approov service as being authentic. So the last step you have to go through is to go ahead and register the app with our service. And when you do that, now you see that the app is being recognized as valid. It's passing a token which is now valid for 5 minutes. That token is being carried with API calls across the secure and PIN channel into the service where it's being verified. So if you were to stop the Approov checking in the back end, you're still sending valid tokens here. They're not being checked, but then neither are the bots. So the bot is back up and active again. Typically in a bring up process, you'll go ahead and start disable, make sure everything's okay, and then go ahead and lock the system down. And as Richard said, you can evolve the security policy over time. So you might start by providing valid tokens if the, let's say, even if the device is jailbroken or rooted, but over time you may decide to tighten that up, and that would just specify sort of the real-time policies that would be used to determine whether an app is considered authentic, running in a safe environment or not. So that's just a quick overview of the Approov service. And let me just wrap it up here real quickly. So you've seen this slide a couple times, and it really is just talking about shifting left versus shielding right, and how you really need both approaches. Shifting left, getting a lot of talk in the press, very important to work out your API vulnerabilities, and you'll get the easy ones early. And as Richard said, there might be some lurking in the background that you never do quite get out, and a hacker could potentially expose those if they exist. So whether you've eliminated vulnerabilities or not, you definitely do need to set up runtime shielding to extend the trust out from your service and encompass everything between the service and the user. That really is what Approov is about, and I hope that we demonstrated that to you today. If you are using the Approov service, and if you've gotten the vulnerabilities out of your backend through other means, you have the other 3 attack services between the service and the user. So you will only succeed in API calls if the app itself is authentic, if the device it's running on is considered safe according to how your security policies are set, and the channel itself will be pinned so that nobody can get in the middle to observe or steal any of the information between the service itself and your application that's running. So at this point, hopefully we've got a few questions, and Richard and I will be glad to answer those.
Okay, thanks, Skip. If you stop sharing, people will be able to see us all. So there's a couple of questions here that are coming in. One is just pretty simple. How long does it take to deploy the service in general? How fast can you deploy the service? So
it depends a little bit on what your front end application environment is, what kind of level of experience. There's sort of a range. We've had customers that have called up with emergencies. They've launched a service and it immediately has been hacked and they're losing money, and they've turned things around in a couple of days. We've had other people with very long, stringent QA processes that have taken a week or so to get things started, then test and qual and run through, and it'll be another couple of weeks before they're releasing into production. So there's a variability there, but basically what you're doing on the front end is just dropping in an SDK. That SDK is lying underneath your networking framework and intercepting your API calls and augmenting them with the tokens. The tokens themselves are fetched automatically from the SDK. The trust is being proven from the SDK. So there really isn't a lot of work to do there, but you are adding another SDK to your mobile environment. On the back end, it really is a standard JOT token type check. So if you are already using something like OAuth 2 for your user authentication, then it's very similar. You're just checking to see, has the token been signed properly by the secret, and is the lifetime of the token still valid, which in our case is every 5 minutes those tokens are going to expire. So very straightforward to do. Does take a little bit of time depending on your level of expertise and confidence, just to make sure everything is right, which is why I mentioned during the demo that you can launch without actually enabling the backend token checking, just to make sure that you are seeing tokens, that they are healthy before you actually start enforcing the attestation that you're getting out of the tool.
There's another question here. So it's a question on false positives. So, you know, are there false positives with the Approov solution, and how is that managed? I guess that means security, you know, false positives. Maybe Richard, you want to?
Yeah, I mean, it's a sort of different model from a WAF type model or a kind of back-end analysis type model, because it's not making probabilistic choices. It's a positive security model, so it's a bit like user authentication. So it's not like you get a false positive on the password being nearly right, if you see what I mean. It's either right or it's not. So we are doing an analysis, and then we're positively showing that we have the right app running, and the environment is free from the things we're looking for. And then you get a positive signal, and then that results, depending on what we find and what the policy is, in a token that is either valid or it's not valid.
Yeah, I just added, it sounds like the questioner is maybe considering other backend solutions that really are focused on analyzing the behavior of the sequence of API calls that they're seeing. And that is definitely a statistical game, and you will get a sequence of false positives. Here we're making a really strong yes/no decision. Either it is an authentic app or it's not. Either the environment is healthy or it's not. Either you can make a pinned connection or you can't. So there aren't really any false positives or negatives to contend with.
There's a question here about the environment where, you know, apps are being used as COVID vaccine passports. Skip, I think you've been involved in a lot of our healthcare work. Do you want to comment on that?
Yeah, so there's quite a bit of work going on in trying to both come up with robust passport type approaches, as well as sort of broad interoperability of things. So there's some work being done over at the Smart Fire organization on standards that are generally being adopted by most of the different players. The security is an issue there. We're already seeing in the marketplace people trying to spoof credentials and to supply vaccine credentials, I guess, on the market for sale. So there are definitely people attacking that. So it is a good example of where the API itself is not flawed necessarily, but it's entirely making sure that you can secure the environment. So it's a great example for API shielding and why it's required. And you know, we're talking to a lot of people about how to do that. You know, even during COVID, not just before the crisis, we have customers that are doing COVID tracking and COVID check-ins that are using this kind of technology to secure everything.
Yeah, we're very active in that space. We're actually members of the VCI initiative, which is focused on securing vaccine passports, and we're also undertaking some substantial research on the FHIR APIs currently, which is the standard that's being used for all of the healthcare API definitions in the US. Okay, we're at the top of the hour or approaching it. So I think we should probably bring this to a conclusion. So actually, we have a special offer for people who've attended the webinar. And Skip, you want to talk a little bit about that?
I was going to try not to offer it, but you know, because we have time, I guess we'll go for it. Okay, so this is our special offer. All right, so if you go to the Approov website,
Sure.
Oh, gosh, you're missing the exciting slide I put up here. Thank you for that. Okay, so if you're still with me, here it is, special offer. If you go to the Approov website, you can go ahead and sign up for an Approov trial. To anybody that wants to sign up, it's free for 30 days. No credit card required. I really feel like I'm shilling here. You just go, you sign up, give us your name and email, and you're in. And you get full access for 30 days to Approov. You can integrate it in with your apps, front ends. You can try it out on the back end, get access to all the telemetry that's going on. But if you are among the first 5 to sign up after this webinar, then we will throw in for free, and I'm sure this is a couple $1,000 value here, a free pre-deployment checklist review. So Richard or myself or both of us or some of the other guys on our team will sit down and walk through and have a conversation with you about what security policies you're doing, and we'll work through a checklist, talk to you about recommendations, analyze your existing system, whatever you want. So we'll go through and walk through that. We have a pretty well-defined way of walking through this with customers. So when you do sign up, if you go and click on the free trial button, it'll take you to a multi-step form. And the last step before you click OK, just add API webinar in the other information box. We will see that. And if you're among the top 5, then we will be glad to sit down and work with you. Maybe if you're in the top 10 too. We enjoy actually talking about security with people. So we'll be pretty flexible with that, I'm sure. Back to you, George.
All right, well, thanks. That's it for today. Thanks for attending. Thanks for your participation. Thanks for the questions, and we'll speak to you all soon. Thanks.
Okay, thank you.
Thanks, everybody.
Thanks.